Response surface methodology is a statistical technique utilized for modeling and optimizing the interaction between many input factors and a response output. It is utilized frequently in product design, engineering, and process optimization projects. In the context of Lean Six Sigma, RSM can help improve processes by identifying the key inputs that influence a process's output and defining the optimal values of these inputs to reach the desired level of process performance. The link between inputs and outcomes is modeled using a combination of regression analysis, design of experiments, and optimization techniques. RSM aims to build a mathematical representation of the link between inputs and outputs, which is then utilized to optimize the process and find the optimal operating conditions. RSM can be utilized in numerous process improvement projects, including those in product design, engineering, and quality assurance. RSM has various advantages for Lean Six Sigma process improvement projects. First, RSM can assist in identifying the important inputs that influence the output of a process, enabling the process to be optimized and enhanced. Second, RSM can be used to determine the ideal operating parameters for a process, which can result in enhanced process performance and increased productivity. Thirdly, RSM is capable of providing a visual depiction of the link between inputs and outputs, which can aid in communicating the results of the study to stakeholders. It is essential to emphasize, however, that RSM is not a one-size-fits-all solution, and that the choice of RSM approach should be based on the specific needs of the process improvement project. In addition, RSM necessitates a solid grasp of statistical methodologies and the utilization of specialized software, which might be a hurdle for some firms. For a product management company, the creation of a new product would be an example of RSM's application. RSM could be used to optimize the relationship between numerous design inputs, including material selection, production processes, and design parameters, and the response output, including product cost, weight, and strength. The objective of the RSM analysis would be to discover the optimal input combination that would result in the target product performance. In conclusion, RSM can be a useful tool for Lean Six Sigma process improvement projects, aiding firms in optimizing processes and achieving enhanced performance. To make the most of RSM, it is essential, however, to thoroughly assess the requirements of each process improvement project and to have a solid grasp of statistical methodologies and tools. Another example of RSM usage in a Lean Six Sigma process improvement project would be in manufacturing. For instance, a producer of plastic components may wish to enhance the efficiency of their molding process. Several input variables, including temperature, pressure, and cycle time, influence the molding process's response output, which includes component quality, consistency, and production rate. Using RSM, the manufacturer could run a design of experiments to determine the link between the input variables and the output response. The dough would involve modifying the input variables in a methodical manner to determine their influence on the output response. The results of the dough would then be examined using regression analysis to develop a mathematical model illustrating the link between inputs and outputs. The producer might then employ optimization techniques, such as surface response plots, to establish the molding process optimal operating conditions. The best conditions would be those that produce the required process performance, including high-quality parts, consistent manufacturing, and a high production rate. Utilizing RSM, the manufacturer was able to optimize the molding process, resulting in enhanced process performance, increased efficiency, and decreased costs. This example illustrates the potential for RSM to support Lean Six Sigma process improvement projects by assisting organizations in identifying critical inputs, determining optimal operating conditions, and enhancing process performance.